Okay, so let's work through a practice problem that involves this idea of mass defect and binding energy. Let's say we have thorium-228. And thorium-228, or thorium, is atomic number 90. And let's say that it undergoes alpha decay. Whoops. And so when a nucleus undergoes alpha decay, remember that we are giving up or losing an alpha particle. And then if we have to balance this, if we have 2 alpha 4 here, we have to take that out of our original nucleus. And so our new nucleus has to have 2 fewer protons than our original. So that's going to make it 88. And it has to have an atomic mass that's 4 less than the original. So it's going to have an atomic mass of 224. And if we look at our periodic table, we see that the atomic number 88 is associated with radon. And so here is our balanced nuclear reaction for the alpha decay of thorium-228. If we look up some of the numbers that are associated with this reaction, we're going to find that the mass of a thorium-228 nucleus is going to be equal to 227.97929. And that's atomic mass units, so U's. And then the mass of the alpha particle is equal to 4.00151 atomic mass units, and then the mass of the radon 224 is equal to 223.97189 atomic mass units. Okay, so this is the very specific mass of the product. These are the very specific masses of the reactants. And notice how we're going to 5 decimals here. Okay, because this is such a small amount we're talking about, it's very important that you extend those decimals out a good ways. You can't get accurate numbers if you only use 1 decimal or even 2 decimals. So on most of the masses, you're going to find it out to at least 5 decimal places. And so the next step here is to find the mass difference. And so we're going to add the masses of our products together, 223.97189 plus 4.00151, and what we end up with is a mass of 227.97340. And so again, notice the 5 decimal places, and it takes that many before you start to notice the difference. It's not until the 3rd decimal place that you see a difference between these 2 masses. And so that then takes us to our next step, which is to actually find the difference in mass. And so 227.97929, which again is the mass of the original thorium-228, minus the mass of the 2 products added together, which is 227.97340. And so the mass difference we get is going to be, do this real quick, 12, 8, 5, 0.00589 atomic mass units. This is the mass defect. Okay. So that's the actual mass that's lost. Now we can convert that into the energy, and here we're going to use a pre-calculated relationship, which is that one atomic mass unit is equal to 931.5 mega electron volts. And so if we use this relationship here, 931.5 mega electron volts times 0.00589 U, that's going to give us an energy loss that's equivalent to 5.49 mega electron volts. Okay, now keep in mind then this mega is 10 to the 6th, and so this is 5.49 times 10 to the 6th electron volts. And to kind of continue this through, and just to give you a little more perspective, an electron volt, and again, as I mentioned before, we're going to talk about electron volts more a little bit later on in the year, but just to give you a comparison or an equivalency here, 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. So you see that's a very, very small number. And so this amount of energy in joules, if we do just a little rough estimation, we have 10 to the 6th times 10 to the negative 19th. The energy in joules is on the order of 10 to the negative 13th, which is very, very, very small. And so when we're talking about one nucleus or one reaction like this, we're talking about very, very small energies, which is why the electron volts and the mega electron volts are used.